Hey class, in this recording we are going to be focusing on chronotropic effects and chemicals. So when we think, just to review, if something is a chronotropic agent, it's going to change the heart rate. A positive chronotropic effect is going to increase the heart rate. A negative chronotropic effect is going to lower the heart rate. And our autonomic nervous system typically is not going to initiate heart rate. That's the pacemaker cells within the sinoatrial node. But instead, it's going to modulate the heart rate, both the rhythm and the force of contraction. And as we look at the cardiac centers in our brain, there's a structure in our brain referred to as the reticular formation that is going to branch and travel through the medulla oblongata, and the cardiac centers of the reticular formation in the medulla oblongata are ultimately going to be the parts of the brain that modulate the sinoatrial node and influence the heart rate. If we have a cardiostimulatory effect in play, we'll have some neurons of the cardiac center send signals to the heart via sympathetic pathways. So remember, the sympathetic nervous system is responsible for our fight or flight response, and it's going to help to upregulate heart rate. We also have cardioinhibitory responses or effects, and those are transmitted via the parasympathetic nervous branches, typically through cranial nerve number 10, the vagus nerve. So as we look at our chronotropic effect of the autonomic nervous system, the sympathetic ganglion fibers, postganglionic fibers, are androgenic, which is to say that they are going to respond to norepinephrine and epinephrine. They also are going to release norepinephrine. Then they are going to be able to, that norepinephrine, once it's released, is going to bind to the beta androgenic receptors on the heart. Those beta androgenic fibers on the heart, once they're bound to, are part of a G-coupled protein cascade, and when activated, they will cause there to be a lot of cyclic AMP building up on the inside of the cell. That buildup in cyclic AMP on the inside of the cardiomyocyte is going to cause there to be an increase in the amount of cyclic AMP dependent protein kinases. As we have that increase in the cyclic AMP dependent protein kinases, we find that they cause the calcium channels to open, and as we have more calcium entering into the sarcoplasm of the heart, that increase in calcium is going to cause there to be the opening of the calcium channels within the plasma membrane, and then we have more calcium that's going to bind to troponin, and as troponin has calcium bind to it, we can initiate the cross-bridge cycle, which we talked about in great detail last semester. Ultimately, as we have more norepinephrine and epinephrine make it to the heart, we are going to have an increase in the force of contraction and the speed of contraction, ultimately making our cardiac output increase, and we will have a positive chronotropic effect. Now, as we're looking at those fibers, the increase of calcium ions, particularly to the cells of the sinoatrial node, are going to accelerate the depolarization of the sinoatrial node. And that accelerated depolarization of the sinoatrial node is also going to contribute to an accelerated heart rate. We also find that we can cause contraction to accelerate, and the relaxation phase is accelerated, and that the heart rate can go up to a max of 230 beats per minute, which is quite high. 230 beats per minute assumes that you have a young person in peak physical health under a lot of physical stress. I know for me in particular, when I was a teenager, my heart rate would max out at about 220 beats per minute when I would measure my heart rate while I was working out aggressively. And I guarantee you my heart rate does not get that high anymore. If I get my heart rate up to 160 to 180 beats per minute, I'm usually feeling pretty exerted. I'm huffing and puffing at that point. So as I'm As we look at excessively high heart rates, anything over 180 beats per minute, we find that for most people, distally or diastole becomes so brief that there's not really enough time for adequate filling of the ventricles, and we start to get a diminishing return, where stroke volume goes down because the ventricle doesn't have enough time to fill with blood, and then as stroke volume goes down, cardiac output goes down. Now, as we look at the parasympathetic branch and its effects on the heart, the parasympathetic fibers from the vagus nerve have cholinergic inhibitory effects on both the sinoatrial node and the atrioventricular node. And if it's a cholinergic effect, that means that it's going to respond to acetylcholine. And acetylcholine will bind to a specific kind of receptor known as a muscarinic receptor, named after the genus of mushroom that was initially found to release a chemical that bound to those receptors. And once those muscarinic receptors are activated, potassium gates open in those nodal cells, and as potassium gates open, potassium will rush out of the cells and make it so that it's more negative. Those cells become hyperpolarized, and more calcium and sodium need to leak in order to reach the threshold depolarization voltage. So ultimately, the parasympathetic fibers will lower heart rate. Now, as we look at these cardiac centers, they are going to be constantly modulating our heart rate. And if it wasn't for those cardiac centers, our sinoatrial node, our pacemaker, would typically give us a heart rate of about 100 beats per minute. However, we're always going to be exposed to some vagal tone. Our vagus nerve is going to be constantly exposing our heart to low levels of acetylcholine that will lower our heart rate to 70 or 80 beats per minute when we're resting. And this is because the vagus nerve has a constant, steady effect on us, background firing rate, to help us relax our heart rate. Now, as we look at these cardiac centers, the input centers to the inputs to the medulla oblongata and the cardiac centers within the medulla oblongata are varied. There are many different sources. We can have higher brain centers. So when we say higher brain, we typically think parts of the cerebral cortex. So thinking about a situation can either cause you to relax or cause you to become stressed out. You can have your emotional system, your limbic system, your sex, satiety, and sleep system cause you to have a change in your heart rate. The hypothalamus can also initiate a change in your heart rate. And we can have just a wide variety of other sensory or emotional stimuli. Our medulla oblongata is also going to receive information from our musculoskeletal system, our blood vessels, and our brain stem. And as particularly as we look at the musculoskeletal system, the muscles and joints, we're going to have a lot of proprioceptors. A proprioceptor is a special kind of sensory receptor that lets us know how our body is oriented in space. It gives us our intuitive feel for how the body is oriented. And these proprioceptors, once our body just starts moving, is going to increase our heart rate. Even before we have the increase in the metabolic demands in the muscle tissue, just the moving of our bodies causes our heart rate to go up. Now, another thing that's going to influence the cardioreceptors, or cardiac centers, I should say, are baroreceptors. These are special receptors that measure blood pressure. They are the blood pressure sensors of our body. We have these baroreceptors both in the internal carotid arteries and the aortic arch itself, and these baroreceptors are going to monitor blood pressure to see if it decreases. If we have a decrease in blood pressure, we are going to have to signal for the heart rate. That signal rate from the baroreceptor is going to go down. And as the signal rate goes down, the cardiac centers within our brainstem are going to cause the heart rate to go up. So if blood pressure goes down, ultimately heart rate goes up. And the reverse is true. If our blood pressure increases, the signal rate from those baroreceptors also increases, and then our brainstem will cause the heart rate to decrease in response. So if we have too low blood pressure, we raise our heart rate. If our blood pressure is too high, we lower our heart rate. We also can have chemoreceptors in our bodies influence the cardiac center of our brain. Chemoreceptors are a category of sensory structures that measure chemical concentrations in our bodies, and they can be measuring different kinds of chemicals. The three most common ones are blood pH, blood carbon dioxide concentration, and blood oxygen levels. We find that we have these chemoreceptors located all throughout the body, but the ones that influence the cardiac centers are located within the aortic arch, carotid arteries, and medulla oblongata. We find that these chemoreceptors are going to play a much more important role in regulating our respiratory rhythm than cardiac output or cardiac rate, but they can still influence our cardiac rate, particularly when we have a high amount of CO2. That high amount of CO2 can raise heart rate and help us to prevent acidosis from setting in. In hypoxic situations, low blood oxygen levels, we have the ability to slow down our heart rate to help conserve oxygen. As we look at baroreflexes and chemoreflexes, so reflexive changes in response to blood reflexes related to blood pressure or reflexes related to blood chemical concentrations. These reflexive responses or fluctuations in heart rate have negative feedback loops. So they help to maintain homeostasis, and they help to keep the body around some pre-prescribed set points. Now, as we look at some chemicals that can influence heart rate, these chemicals include autonomic neurotransmitters such as norepinephrine and acetylcholine. So here's norepinephrine up on the top, and then here's the molecular structure, the skeletal structure for acetylcholine. We could also have adrenal hormones present in the blood. So instead of being released from the axon terminal of a neuron, they could be released into the bloodstream. That norepinephrine and epinephrine can increase cardiac output. Here's epinephrine's chemical structure. So as we look at norepinephrine up on top and epinephrine here, the only difference between those two is right there. They are very similar to each other. But that little change on that functional group causes a profound difference in their effect. When we look at other chemicals that can influence heart rate, those other chemicals include nicotine. Nicotine is going to stimulate catecholamine secretion. So if we have nicotine in our blood, ultimately that nicotine will raise heart rate. Thyroid hormone is also going to be able to bind to the androgenic receptors. As you look at thyroid hormone and its physical that was nicotine. As we look at thyroid hormone down here and its physical structure, that thyroid hormone is going to mimic some of the key structures present on both norepinephrine and epinephrine and can activate those same receptors. And then for my personal favorite, caffeine right down here, caffeine will inhibit cyclic AMP breakdown. So then that causes the norepinephrine and epinephrine that we naturally have in our bodies to have a more profound effect. So by having more caffeine in our bodies, we have cyclic AMP last longer, and by making cyclic AMP last longer, we can prolong the effects of the sympathetic nervous system on our bodies. We also have some electrolytes that can influence heart rate. Potassium ions are probably the single greatest ion for regulating heart rate. They have an enormous chronotropic effect. If we have too much potassium in our bodies, too much potassium ions will cause the potassium to diffuse into the cardiomyocytes. And that is going to hyperpolarize the cardiomyocytes, making them less excitable. So too much calcium, hyperkalemia, is going to slow our heart rate down and make it very irregular. And if we have even more potassium building up in our bodies, our heart will eventually cease to beat.
Please, my mom paint.
Ben, I'm making a recording. If we have hypokalemia is not enough potassium, and that causes the cells to become hyperpolarized, and as they are hyperpolarized, we need that increased stimulation. As we look at calcium, too much calcium is known as hypercalcemia, and that's going to cause an increase in heart rate and contraction strength. And hypocalcemia is not enough calcium. That's going to cause a decrease in heart rate and a decrease in contraction strength. And the reason I included this figure over here is because Agatha Christie, her claim to fame is writing murder mystery novels, very good murder mystery novels. One of the characters she talked about is Hercule Poirot, who is the original Adrian Monk, so to speak. He's a very quirky detective, and that has a lot of OCD issues. And in many of his murder mysteries, there are potassium-based poisonings that kill the patients. So that's all we have for this presentation. If you have any questions or comments, please feel free to shoot me an email or post them on the discussion board. And as always, happy studies.